So this is joint work with Shai Moran, who's a postdoc at UCSD and now he's at Berkeley, and also with my student Jiapeng Zhang. And I have to say in advance, so I know very little about machine learning, so everything I know I learned from Shai. So I'm happy to get any feedback. I mean, this is sort of a bit more of a conceptual work. We're trying to suggest some new model for active learning. I'll explain what active learning is, and this is still work in progress. I'm happy to get any feedback that you have on it. Okay. So here's what I plan to talk about. So basically, I don't assume any previous knowledge. So I'll explain what active learning is. I'll give some example when it's useful, and somehow I'll give some example showing that in most cases it's useless. This is in the usual setting it is. It's as a pack learning model. And then I'll suggest a new model and show some properties of it, and then discuss some problems. Okay, so what is active learning? So active learning tries to extend classical, pack learning. So instead of in the usual notion of pack learning and passive learning, you have some learning algorithm that gets some sample of labeled data from some unknown distribution that and try to make predictions on label or on data that they haven't seen. And I'll define all this more formally in the next slide. And somehow in active learning, we separate it to tasks. So we're assuming the algorithm gets lots of unlabeled data, and then whenever you want to ask a label for a specific sample or point, you need to pay $1. And the question is, how can I pay a little bit of money but still learn something useful about the overall class? And this is motivated by a lot of real-world problems where it's much, much easier to get unlabeled data rather than labeled data. So unlabeled data just accumulating documents, let's say, and labeling actually requires a person to go and say, is this document about politics or about sports or whatever type of classification problem you're trying to solve. But for us, we just care about the theoretical part of it. So let's make some definitions. So in this talk, I will only focus on something called the realizable case, if you know what these things are. So what do we have in machine learning? With a classification problem, you have some domain X, and you have some labels Y. And for us, for the most part, the labels are just going to be 0, 1, so a binary classification problem. There is some unknown distribution over the domain that you don't know. And there's also some concept class that encodes all the potential ways of giving labels to points. And so maybe one example to have in mind is threshold or half spaces. So you can think of maybe my space is R to the D. There is some unknown distribution on it, and the classifications are all this. So here Y would be 0, 1, and all these functions from X to Y, such that C of X is basically the sign of maybe AX plus B. So this is one very important canonical example for concept classes, all the thresholds in some high dimensions. And there's some unknown concept of data and that you don't know, you're trying to discover. And this notion of realizable case
will be a one half.
Yeah, so a concept here will be one of these half spaces, and realizable just means there's no errors. There's also something called the agnostic case where there are errors. So I will not discuss this in this talk today for simplicity. I just focus about the realizable case.
Okay. So you didn't say, but one gets a sequence of independent points.
Yes. So I'm going to say it in the next slide. Yeah. So this is just a general setup. So now what is a learning problem? So this is a passive learning algorithm. So I just copied from the previous slide. Now what is a passive learning algorithm? The standard pack learning model. You obtain labeled samples, sampled independently from your unknown distribution. So what is a labeled sample? It's a pair X, Y. X is sampled independently from the distribution. Y is labeled according to this unknown concept, so this threshold in this example. And so you have your algorithm, it gets all these examples, and at some point you need to make a prediction on the entire space. So this is called the hypothesis, so it outputs some function from X to Y. If it's a proper algorithm, that this H is one of your concepts, it could maybe be another hypothesis outside the concept, but the goal is to be as correct as possible. You want to minimize all the mistakes that this algorithm makes, and formally, so you want to minimize something called the loss of this algorithm, which is what's the probability over this distribution that you don't know, that your prediction, the hypothesis, is different than the unknown concept that you don't know. Okay, so this is a classical pack learning setup.
So you don't know, but you are tested on the same distribution.
Yes, exactly. You are tested on the same distribution from which you get samples. Okay. So, but if there are any questions, then stop me and ask. I mean, this is, like I said, this is a bit of a conceptual talk. I mean, there won't be a lot of technical details here, so please stop me and ask if you don't understand anything. So what is active learning? So we're sort of trying to refine this model and say, well, we do it in 2 steps. So the algorithm first gets only unlabeled data from the same distribution. So we sample, it could be ordered, not ordered, doesn't really matter. So you get this sort of, unlabeled sample points, x1, x2 up to xn, coming from this unknown distribution. But then the algorithm can sort of, pay to get labels. So whenever the algorithm chooses to get a label of some point x5, it sort of would query some oracle. This oracle would label x5 with y5 according to this unknown concept, and then it charges the algorithm $1. And sort of the goal is, can we sort of still get meaningful algorithms, but with sort of only label a few of the points? So this is sort of the premise of active learning. Okay? Can we get the same performance as passive learning while only seeing a few labels? Okay, problem is clear. Good. So I'll sort of focus on a few things here just to make my life a bit easier. So first, I'll assume that the labels are all 0, 1. Now, it's not really needed for what I'm going to say, just going to sort of slightly simplify things. Like I said, it's a realizable case. And also, I'm assuming that the algorithm doesn't know the distribution, doesn't know the concept, so this is called the prior free case. I mention it here because, as you'll see later, a lot of the work in this area is actually when you assume that you know something about the distribution and you know something about the concept, because there are a lot of examples showing that you cannot do much without some assumptions. And he will make a different assumption. Okay.
You mean not the concept class? You know the concept.
I know the concept class, but I don't know anything about the concept with any potential threshold, and I don't know anything about the distribution. Right? Okay.
If I completely knew the distribution, then active learning is not different at all from passive learning, right?
Yeah, if you knew the distribution, you can do you can do much more somehow. This is just statistics. I mean, the way I understand the difference between statistics and machine learning is that somehow in statistics you know something about the distribution, while in machine learning you know nothing, right? So this is the way at least I visualize it. But anyways.
Learning was invented by statisticians.
No, not. I say like hypothesis testing with statistics, to be more precise.
Unlabeled data,
Yes.
don't generate myself.
What?
I guess I'm saying that if I knew the distribution,
Mhm.
I could generate the unlabeled data just myself.
Exactly,
So
exactly.
in some sense, the active setting.
But you can
No.
query.
But you can query, right? You don't know the labels, right?
I see, okay.
Yeah. But somehow also if you know the distribution, you can do more things. Yeah. So part of the challenge here that you don't know the distribution. So somehow I'll make another simplified assumption, which is sort of like the way I presented the problem before is that you get these labels and you want to make good predictions on them, but you could sort of use sort of standard generalization bounds like VC dimension bounds to say that it's equivalent to the following problem. Let's say I want to learn and at the end only make mistakes on epsilon fractions of the points I haven't seen. It's equivalent to the following problem. Get a large enough sample, predict it without any mistake, and this generalizes to the overall distribution. So if you've ever seen, VC type bounds, then you get this type of behavior. So instead of I want to sort of restrict my attention to the following problem, that I get a large enough sample of size roughly 1 over epsilon, and this one maybe need to replace by the VC dimension of the class, but I'll mostly focus on the depends on epsilon here. As the error got smaller, how many more samples do I need? So I need roughly 1 over epsilon unlabeled data points. I want to label a few of them, and I want to be able to predict all of them correctly. And if you can do that, and you're proper, then somehow you can predict the entire class with arrow epsilon. So I'll assume this
Yeah, do
for now.
that means find any arbitrary element in the concept class that is consistent.
Yes,
Like
yes. Exactly, yes. Okay. But now the challenge here, I'm only allowing you a few label points, right? Yes. Okay. So I'll just focus on this task from now on, so you forget from now on about errors. The challenge is the following. I gave you some large enough sample points of unlabeled data. You want to ask for a few labels and predict all of them correctly.
So now you return something from the concept.
Yeah, and I want to return something from the concept class, yes. And it's proper learning because we're assuming that we're in this realizable case, so you can always do proper learning because, at least information theoretically, right? Because there is always one concept, even more.
So you don't care about efficiency?
No, I won't care about efficiency. I will care, but let's say for now we don't care about efficiency. Okay, just information theoretic. Okay. So instead of, I want to just make one small comment here that somehow typically this generalization bounds assume something like VC dimension bounds, And if you assume that your label set is not 0, 1, but it's very large, then somehow, yes? Sorry.
I just want to ask, is there a danger that like in being correct on the sample, you overfit and make...
Exactly. You can do that, right? If your sample is small enough, it's very easy to make predictions that are correct on the sample set, but they are completely wrong on everything else, right? But somehow if you know something about your concept class, like for example, it has a low VC dimension, then and your sample is large enough, then this doesn't happen with high probability. So this is the premise of basically VC dimension pack learning type arguments.
When the D dimension, the VC dimension
Is D.
So if you take sufficiently 100 D points, then if you have a consistent thing, your error will be
1%. Yeah. Roughly. So I want to make just again, so this last comment at the end is somehow if the label set is very large, then what we do would still work even if you don't have VC dimension bound. So you can sort of replace VC dimension bounds in some contexts, even if the label set is large. And in general, there are these questions that we don't really have a good combinatorial understanding of what replaces a VC dimension once the label set is large. But that's I will not address this here. Okay. So this is just a side comment.
It's important, Aaron, also that he's assuming that there is one such
Yes.
class. There's some, what do you call it?
Concept class.
Actually is the right answer.
Yes.
The data behaves in such a way that like.
Exactly. But this generalization bounds also follows in the agnostic case, right? So you don't have to assume realizable for that. You need a bit more sample point, but it also works in the agnostic case. Okay. Okay. Any more questions? It's good that you ask questions. Yeah. So now let me give you one example where you can do it, and it sort of shows you this power of active learning. But unfortunately, this is more or less the only example where it works. And sort of this and a few other similar examples is where it works, and everywhere else it fails. Which is sort of why people, to some extent, give up on active learning without making more assumptions. Okay, so what is this example? It's thresholds in one dimension. So it's like this problem, but when D is 1. Right? Okay. So D is 1. So basically what you get points in R, on the real line, and you get these labels. They're 0 or 1 as follows. So, there is some threshold T that you don't know, right? That's your hidden concept. And if xi is more than T, you label it 1, and if it's less than T, you label it 0. Okay? And your goal is sort of to find T, basically, right? So remember, a challenge now is I give you this n sample points, and you want to predict all of them correctly. And if n is large enough and you can do it, this sort of promises it can generalize to the unknown distribution that you have. So how can we do it? And the answer, this is very simple. Just do binary search, right? Here you can sort of do things much better than query all the points. Right, so what do you do? So I don't know the label, so I just take the middle point. Let's say it's 1. So I know that all of these have to be 1, right? Then I take the middle point of the one I don't know. So let's say it's 0. I know that all the points to the left of it must be 0 and so on, right? So this is what we get. So okay. Right, this is very simple. So binary search performs great. We just need to query log n labels, and we can sort of by ourselves infer the rest, right? So we don't have to pay this n dollars. We just pay log n dollars. And so you see that, and so you get very excited and say, well, maybe I can do it, in general. And somehow the answer is no. In most interesting classes, this fails, because there are counterexamples where you cannot do this. So let me show you one example, which is doing this in 2 dimensions. Only there it fails. And sort of, unfortunately, most concept classes look like that. They don't look like the one-dimensional case. So we have, again, just to repeat the question, so it's a very similar question, except now in 2 dimensions instead of 1 dimension. So you have these points in 2 dimensions, coming from some unknown distribution, but let's ignore that. Labels, again, 0, 1 as follows. So there is some threshold in 2 dimensions that you don't know. There is some line that separates them, and you don't know what this line is, and you want to predict all of them correctly. You're not allowed any mistakes. And so how can we do it? Well, we can't. Here's an example showing you cannot do it. Let's say all these points sort of lie on a circle, right? And only I give this promise. One of them is above the line, the rest are below the line. How would you find out which one is which? You can't. You have to query all of them, right? You can't really. There's no smart way to avoid this. And even if you try to sort of, play with the model and say, I just want to make some errors, all of that, it doesn't work. This is the canonical example where you cannot do active learning without some additional assumption, okay, or giving this model some more power. Okay, this clear? So this is a picture you have in your mind when you think why active learning is impossible without more assumptions.
So
Yes.
Gupta has actually a characterization of
The Discrete doesn't have it, but there have been follow-up works by Henneke and some others that give some characterization. And we also can give some characterization. But unfortunately, it seems this characterization is it's very interesting on the combinatorial side, but on the application side, it's very weak because for most classes, the answer is you can't do it without some more assumptions. Okay, so how do people handle that? So most of the work so far has been on adding more assumptions to the model. So either you do some average case analysis, assuming something about the distribution, the distribution is nice in some way, or you give some restrictions on what, like for example, you could say maybe the distribution is Gaussian, or maybe things are separated. So you make some more assumptions about the model, right? And then you get out of this very concrete, specific question that some of them you can solve and do better. There's been a very interesting line of work on sort of distribution and target concept dependent things. In particular, this work of Balkan, Hanneke, and Vod that showed that somehow, in general, classes with bounded VC dimension, you can do something better than passive learning that somehow depends on the concept, but you don't know how it depends on it. So somehow, but you can sort of think of an oracle that tells you, for every concept, there is a way to improve over passive learning. But again, sort of it's very weak, and most of the works are about sort of things that are much more concrete distributions, concrete assumptions about the model. And sort of we want to step away from it. We want to make some other assumption that is sort of context independent, that doesn't assume something about this distribution, but that still allows you more power. So somehow the algorithm should get more power. And basically what we're suggesting is just to sort of allow other types of queries. So, but somehow we want to make them restricted, right? So, like with thresholds, I want to, maybe you're allowed to ask about other points, but you should not ask arbitrary general questions about the things that have nothing to do with thresholds, right? Or maybe the point that you query about should somehow depend on the point that you've seen. So I'll define this more formally later, but somehow to allow some types of restricted membership queries beyond the sample points that you've seen. So for example, if you go here to this example, so maybe it makes sense to ask about points here, right? Maybe that's going to help you because it sort of separates things more. But the question is, if you do that, can you still promise generalization? And in general, the answer is no. But if you make this be simple enough, then the answer is yes. Then you still can get generalization in the same way that you get from VC dimension bounds. OK. So I'll explain restricted in a second. It will come from some communication complexity type of definition. We'll define some communication game that sort of will limit the power of an algorithm. And it, in some cases, will capture some notion of some intuitive notion of restricted. But we don't really have a precise characterization here. But the nice thing here that what we can show is that whenever you can define these sort of restricted models, you go back to the one-dimensional case, in the sense that you can still just perform log n queries, label queries, and still recover all the points. Okay, so you sort of go back to this full power by allowing these sort of slightly more general queries. So I'll explain it sort of, and again, I mean, this is what happens if you care about errors, but let's ignore that for now. So let me sort of give you this example. So let's go back to this example of half planes in 2 dimensions, and we'll allow these new types of queries, and I'll show you why we can sort of go back to like logarithmic number of label queries. So again, just to repeat the question, so we have endpoints in R2. The label is just given some unknown threshold in 2 dimensions, and you want to predict which ones lie above and below the line. And you don't want to make any mistakes. And now the goal is to make as few label queries as possible and still correctly label all of them. And what we will allow now is also to do comparison queries. So what are comparison queries? So if I give you 2 points, xi and xj, I allow also query which one is closer to the line. Okay, so what do I mean? So we have these points here in 2 dimensions. There's this line that you don't know. So I will also allow you to ask questions like which one of these points is closer to the line. Well, you don't know the line, but sort of which one is closer. And you can think of this as maybe making sense because what would that mean? It means that sort of if you want to apply these type of ideas in a real setting, let's say. So let's say you want to label you see pictures of digits and you want to label them either like 0 or 1, let's say, right? Just to make it binary. So you can ask a person, is this 0 or is this 1? Or you could give them 2 pictures of 0, which one looks closer to a 0, right? These are comparison of 2 points. So maybe it makes sense also in some applied settings, but for us, we'll allow this here. And so we'll see that this actually allows you to do active learning with log n queries. instead of n queries. So what's the idea? So it's like a proof by picture. So initially we have this unlabeled input of size n that's big, and there's this green line that we don't really know. So we see all these black points, we know them, they came from our distribution, we want to predict their labels, but we don't know the green line. This is just for us, for like, the readers. So first step is we just take a random sample of size 40, a constant size. In fact, 40 is enough here. So we took this small constant size sample of the points randomly. We're going to label them, which we can do with like 40 queries, so it's still small. And then we're going to ask which one of the red points is closer to the line, which one of the blue points is closer to the line. So, we found that we can compare all pairs of points. We just find the red point closest to the line and the blue point closest to the line from our small sample. And then we're going to do the following weird thing. We're going to
compare all pairs. It's a linear.
Yeah, just or n log n. Yeah, just to find the small one, yes. Smallest one, yes. I agree. But 40 is constant, so we don't care, right? 40 is really 40. It's not okay. So, and then we do the following weird thing. We build cones. So what do I mean by that? So I take these red points and I look at their convex hull. And this is the closest point. And I build this cone that goes from this closest point to the nearest point on the convex hull on the right side and on the left side. And I do the same thing for the blue points. So why did I do that? So the claim is that basically I can now forget about all the other points. It must be that any point that belongs to this cone must be red. And any point that belongs to this point, this cone, must be blue. You can't make mistakes. So somehow, although I don't know where the green line is, I know something about the family of all potential green lines. Any potential line that separates these 3 points from these 3 points, where this point is the closest between these two, and this point is the closest between these two, cannot intersect this region, and it cannot intersect this region. So now what I know about the green line, it comes from this family of green lines that sort of separates this red region from the blue region. Okay? So I won't prove it, but it's a simple geometric exercise. So now what we can do, now we're happy. Say, well, all the points here are red, and all the points here are blue. So we got this for free. Right? So all these points here are red, all the points here are blue. Just delete them, and then repeat. Okay? So that's the algorithm. Okay? Any questions about the algorithm? Right? Just repeat this until you label all the points. Okay. Yes?
I guess I'm curious, in this particular example, is it necessary to have this closest query? Because I'm wondering, would it be possible to first use binary search? If you choose which points to query, first use binary search to go on one line and say directly here, and then use binary search on the direction to say.
So I'm not sure if so you say so you have this. Okay, let's say you have this sample. So what do you want to do?
I guess I'm saying let's say you don't have a sample at all. You can just choose. I guess you're not allowed to choose arbitrary points.
You're allowed to do whatever you want. Okay. So I said don't do a sample, do something else. But then what do I want? So but then for most points I don't even know their label. I don't know if they're below the line or above the line. So originally I have this unlabeled data, right? So here I only label this tiny sample of size 40. So you want to use this label, this sample, or you want to use other points? Or what are you suggesting?
I was asking if you can choose arbitrary points and get their label.
Yeah, you can do it. Yeah, sure.
But you can't create new points. If you could, then you could do binary search, but you can't.
So it's not entirely true. So if you knew that your family of lines was a finite family of lines, then you can do what you're suggesting. But since you have all lines, you can't easily do binary search. So as you'll see later, this actually translates to a problem where sort of binary search is not clear how to do
I
it.
could poke new black points. I could
Yes.
just, in the dual space, you could just,
Mm-hmm.
every time you add a line that bisects your region, so.
But the question at some point, you have this family of lines, and could I find a point where it gives you a lot of information? So it's not so clear. You'll see later why. It seems that you can always do it, but it's not so.
Only if you can create new points.
And even if you're allowed to create new points, even then it's not so clear. For 2 dimensions you can do it, but for higher dimensions it's not so clear. But because there are some special things about 2 dimensions. But you'll see later why. Think about it. You'll see later why. It seems a priori that you can always do it, but you can't. It's not so clear. Anyway, that's the algorithm. Okay. So now that we want to analyze this algorithm. So the question is, how many iterations do we have to do here? And here's the main lemma, right? So you choose this random sample of size 40, And we chose 40 to be large enough so that with probability 50%, it sort of is useful in the following sense. Right? You're going to label correctly at least half of the point that you're not sure about the label, right, that are unlabeled. So when we do this sort of process, here, with good probability between here and here, we're going to see 50% of the unlabeled points. Okay, so that's a lemma. And obviously, if you can prove this lemma, then with log n rounds, we're done. In each round, we queried some constant number of queries, so we're happy. So now I just want to prove this lemma. So I'll first show this proof of this lemma. It will seem very ad hoc to this problem, but then I will show that this is really an instance of a much, much more general framework that we call active compression schemes that has nothing to do with geometry. It's just a general communication problem. But first I'll show this proof of this lemma in this concrete setting. So again, this is what we want to prove, that somehow with good probability, each iteration is going to label a good fraction of the unlabeled points. So what do we have? So we have these cones. So what do they define? They define what I call a partial hypothesis. So it labels some part of the domain, and some part it leaves unlabeled, right? So the point in the red cone we're going to label, let's say, 0. The point in the blue cone I'm going to label 1, and the rest I'm going to say I don't know. And sort of main observation that we use here, because we're in this realizable case, is that it cannot make mistakes. It might abstain. It might say I don't know. But whenever this hypothesis says it's 0, it must be 0. And there is this geometric, argument that I haven't proved that, if this red point is the closest one to the green line, then and these 2 points have the same label, then your line cannot intersect this region. Okay. And also, we never make mistakes inside or outside the sample, right? But we might abstain. And so we might abstain outside the sample, and the worst case is where we abstain, in all the points outside the sample, but somehow, at least our sample is labeled correctly. Right, so the sample is labeled correctly because we labeled manually all the sample, and our hypothesis is guaranteed to do it, to be correct on our sample, and it never makes mistakes. And I claim this is all that you really need to know. So there's nothing more geometric, there's nothing else geometric that you need to know about this problem. So how can we analyze this? So let me first show you a simpler analysis, and then I'll show you a slightly more refined one. So what is a partial hypothesis here? How do I define these cones? Do I need to know the entire sample? Right? So for example, to define this red cone, how many points do I need to know from the sample? Only 3 points, right? And similar for this blue cone. So I only need 6 points. And I also need some side information. For example, I need to know which one is red from these 6 points, which one is red, which one is blue, and that this point is the closest between these 2 points, right? So I need some side information, and I need 6 points from my sample. And it's just the calculation. This side information, in this concrete example, you can encode using 10 bits. Okay? So there's some constants that sort of 6 points and 10 bits discover this hypothesis. So why is this useful? Well, I can say, well, then, what's the total number of possible hypotheses you could potentially have everywhere? N to the 6, right? There are n points. The number of 6 tuples is n to the 6. The other number of side information is constant, so n to the 6. Let's say a hypothesis is bad if it labels less than half of the points in my original n point data. So what's the probability that a bad hypothesis labels my sample correctly? Well, it's 2 to the minus s, right? Because s is chosen randomly. They choose randomly s points. This labels only half the point, so the probability I'm going to label correctly or label all of s is 2 to the minus s. Right? So by the union bound, I can take s to be of size log n, and I'm done. Right? So this is not what so previously I promised you s is a constant size, 40. But this is like a simpler analysis to get log n. Right? So any questions about this? This is very simple. Right? Okay. So now I'll show you how to reduce s to be a constant.
If the visit dimension is constant.
So here the visit dimension is 2.
No, you can get the sample to be a constant.
Exactly. So this is the same flavor of arguments as visit dimension. But it won't directly use visit dimension. Yeah. So let's S now be a random sample of size m, and m is going to be 40 at the end. Okay. What is a partial hypothesis? Well, it depends. It really doesn't depend on my sample. It depends on 2 things: t, which is a sample of size 6 points, and some side information they call b here, of size of 10 bits, right? So once I got my sample, I did my all the calculations or the labeling. I could extract 6 points and 10 bits of side information that together completely specify my hypothesis. Okay? So T is some subset of 6 points, right, of my original sample. So I here just indicates the indices of these M points. So I can just union bound, not over S, but somehow over the choices of B, which is 10 bits, and I, which is 6 out of these M points. And so the main observation here is the following. If I fix B and I fix I, so I know that my hypothesis depends on the point number in coordinates 1, 5, 7, and 17. It's independent of the rest of the points in my sample, right? They don't, once I tell you your hypothesis in the future is only going to depend on points 1, 5, and 17, then it's independent of point number 2 and 3 and 4 and so on, right? So you can use them to sort of test my hypothesis in the same way that we used originally, the whole points. So it's independent of these points. So the probability that H is bad and labels all of S is now 2 to the minus M minus 6. Why M minus 6? Because I have M minus 6 points remaining in my sample points that are not dependent on Xi, that are not part of these Xi's. And that's just union bound over all of them. So you have this sort of simple calculations. So if you've ever seen VC dimension type calculation, this is a very similar type calculation, except here we don't really use VC dimension directly. What we use is this, and we'll see later, this is called the compression argument, that you can just specify a hypothesis using a small subsample of my points and some side information.
And this is also classical, bypassing, replacing VC dimension by compression.
Exactly. I'll talk about this. Yes. Yeah, if you know it, then you know it, and if not, then I'll describe it later. Yeah. So just sort of to describe this algorithm again. So each iteration was very, very simple. You sample 40 points, you query them, sort of labels plus comparisons. We designed something, let me give it a name. It's a confident partial hypothesis. So it's a partial hypothesis, so it's allowed to abstain. But whenever it makes a prediction, it must be correct. And here we're sort of, crucially relying on the assumption this is a realizable case. So there is a true concept that makes no mistakes. And also it is required to label all the sample of size 40 correctly. And it sort of, then we remove these label points and repeat, and the analysis was just somehow the fact that this partial hypothesis, you don't really need all the sample points. You just need a few points and some side information. Okay? And this is sort of what I want to sort of make a use of in a general case. Yes?
I guess I'd like to ask, so it seems like the argument requires that when you sample, you'll have at least a few points, which you always have at least a few points which are red and a few points which are blue.
Mm-hmm. No, because let's say all the points are blue, then I don't care. Yeah.
Relative to some distribution. You will also be good, if your distribution always gives you points above the line,
Then
that's fine. You'll never get blue points, but
so what?
it's only
Yes.
also the queries that you'll get later to be correct on will also be above the line.
Yes, exactly.
Ah.
Exactly. Yes. So this is the first for this generalization bound, saying, if you never get points that are so far away, then you don't need to sort of predict them correctly. So what is the general framework here? Is sort of something called active compression schemes that of generalize this classical work on compression schemes that is related to pack learning, standard pack learning. So what are sample compression schemes? So they were introduced by Littlestone and Wormuth about 20-some years ago, or no, 30 years actually. And they conjecture that pack learning, standard pack learning, can be characterized by a communication game that they called sample compression schemes. And this was proved last year in so there was this work also of Avi and Shai and Amir and who? And Amir. But this sort of closed that this. They proved this in a more precise sense that this is true. So we still, I'm saying at least quantitatively, because there are some conjectures, some very tight bounds between the size of the compression that I haven't defined yet and the VC dimension. So they still do some exponential gap here, but it's still a constant that goes to a constant.
Learnability was proved actually by boosting much of
But you don't. But you don't get compression.
Yeah, I know, but like what they showed is okay.
Yeah, but no. But
the fact that compression leads to learnability.
no, that is true. But the fact that pack learning implies compressibility, so I think they already proved this, right?
The bound of D log M was already existed,
no,
and that's
no,
enough.
no,
I agree.
For learnability, it's enough.
Yeah, it's enough. Anything below n is enough. But yeah, that's true. D log n implies learnability is enough. But so the conjecture was, can you sort of capture constant VC dimension by constant size compression classes? Yes. Okay. Yes. Yeah, but you're right. And somehow here we just sort of generalize these notions to active learning. And there has been works on this active learning version of this called version space compression, which sort of doesn't allow for more queries than the original label queries. And sort of one of the, I would say, realization of this work that somehow you cannot do much without more assumptions. Sort of this, the concept classes for which active learning is useful, where you don't make any assumptions or additional queries or anything like that, are very, very restricted. Like there's slight generalizations of thresholds in one dimension, but nothing more than that. So let me sort of define these active compression schemes. So you get as an input some unlabeled sample S from the original input. So again, think of S as being of size whatever, 40 or something large enough to make this to work. So there are two players here, the compressor and a reconstructor. The compressor sees S, sees a sample. It can query all the points, inside, outside the sample. It can maybe make some other, membership queries, make whichever query you allow it to make, right? This depends on your model. So it can make other queries if it wishes to. But then what it does is it says, well, after I've seen all this information, I want to somehow select a small sample of my points, the important points, like the ones defined in the cones, and some side information, and I want to send only this to a reconstructor. And ideally, to make this useful, you want this T and B to be much, much smaller than the original sample that he saw. Like, we saw 40 points in our sample, but we only sent 6 points to the reconstructor. So it should be less. And then the reconstructor receives T and B from the compressor, but it doesn't know S, right? So that's crucial. The reconstructor doesn't know the points where he's supposed to predict, make correct predictions. But still, he's allowed to query maybe some more points, but he doesn't know S, so somehow he can only query points given this information that he knows. And then he outputs a partial hypothesis from our domain to Y. Or in our case, Y is 0, 1, but in general, Y or I don't know. And this partial hypothesis depends on the point that he got and the side information, and maybe the query that he made. And what is the requirements? Well, it has to be confident. So we're in this realizable case. Whenever it makes a prediction, it must be exactly the correct prediction. Okay? And also, it should label all this sample S correctly. So, if somehow this reconstructor knew S, then he could just say, I label S and I don't know. And that's it. I'm not labeling anything else. But, and actually, this here doesn't even have to be proper. It could be any hypothesis that you allow it. But it doesn't know S. That's the challenge. It doesn't know S, and somehow this should convey enough information to know the values of on S. Okay?
So the labels of T and the side information should information theoretically contain all the labels of S.
Almost. The labels of T and the labels you can ask about knowing T.
Yeah.
So like you're allowed to compare 2 points in T, for example, right? So you're allowed to do a bit more. So that's a game, right? So we have this. So let's just show this game in this example that we saw. So our sample size was 40. The compressor queries labels plus which one is close to the line. And then you only send 6 points and then 10 bits of side information. Okay? So the reconstructor receives T and B. Let's say that it designs this partial hypothesis. Just depends on these 6 points in the side information, which one is close to the line. And the promise is that it's confident. So this must be red, this must be blue. This is, let's say, below or above the line. Has to be. It labels all of S, but it's allowed to abstain on points outside the sample. Okay? And what is the general theorem here? It's the following. Again, we have this communication game. So we define the cost of this game as just the size of T plus the size of B, just to simplify life. You could optimize it, but let's just simplify life. Take the size of T plus the size of B. If this cost is less than some constant m over 6, if this sample has m points, but you only send m over 6 bits of information, not bits, but sort of m over 6 cost to the other side, then you can do active learning with like logarithmic number of queries. So again, just to make this precise, there's some concept class. We want to correctly label a sample of size n. And if you can find some constant m, where you can design for this m an active compression scheme whose cost is less than m over 6, and it queries some number of points, it could be very large, but it only depends on m. M is 40, right? For example. Then for every n, you can design an active learning algorithm that queries roughly log n queries and labels all the n input points correctly. And the algorithm is basically the same thing that we've done last time. You take a random sample of size m, you run this active compression scheme, and then you argue in exactly the same way that you want to label correctly half the points.
What
Yes.
is the type of queries that I'm allowed to
It's whatever you allow it to do it. So this active compression scheme, this depends on your model. You can decide that you want to allow these queries or that queries or whatever you want to allow.
I give you a set of queries
that you allow.
And you give me a
Yes.
compression algorithm.
Yes, so whatever you allow. Right.
The communication will depend on the
Yes.
query.
Some if your queries are useless, I will need to send all the sample. Right? But if you allow me useful queries, then you can sort of compress things. Right? This is really in some sense, context independent. I mean, it's up to you. It's up to the algorithm designer. And the proof is exactly the same thing as before. I mean, there was nothing special there about half planes, right? So it was just the fact that we need 6 points plus some side information. So now let's do an example. Let's try to generalize this to d dimensions, and then Mark, you'll see why things are not so simple. Even in 3 dimensions, it's not so simple. So now what's our goal? Our goal is to active learn in d dimensions. And just to simplify my life, I'm going to restrict to the homogeneous case. So threshold, the hyperplanes have to go through 0. And this is, by increasing the dimension by 1, you can always assume it. So let me just assume that. So what do we have? So we have these sample points, x1 up to xm in RD. Again, m is like 40 or whatever size of sample you need. And there is some unknown threshold, some hyperplane w star. And I want to predict all these signs, xi in the product w star. Right? That's my goal. What is an active compression scheme in this context? I want to query these points. But now I'm also allowing to query other points that are outside the sample. So I'm allowing to query any point that you want. Let's say for now, right? Choose whichever arbitrary point you want to query. And somehow a few sample points plus some side information should somehow allow us to predict it, what's going on here. So what do we need to predict? Predict means that given a few sample points, like x1, x5, x17, and some side information, there's going to be a set W of all the possible hyperplanes consistent with this information, right? It should contain the real hyperplane, and any point here should correctly label my sample. So again, this generalizes what we saw before. So I'm not able to predict W star from this, but I know that there is this family of potential hypotheses. All of them are correct on my sample, and the real one is one of them. Okay? Okay, that's clear? I mean, that's maybe a bit delicate. And somehow, the point, why do we need all these weird conditions? Because whenever we see a prediction based on this W, and all of these W's are consistent with each other, then we know it has to be correct, right? Our goal was to get this confident partial hypothesis. So how do we predict the label of X? We say it's Y if all of them agree. If for all W and W, the sign is always Y, right? This was in this example of this right here. So here.
This is the description of what you want or what you do.
This is what I want.
I
want some way.
To compute such a W.
I want some way to query a few points, maybe a total sample, and at the end, compute some set W. Think about some, maybe convex set or something like that, of potential hypotheses that contain the real one, but all of them correctly label all my sample points. And how I'm going to make a prediction if I give you a point X, and all the possible W's here, all the possible hypotheses agree on this point, then I know the label, right? If it's below all of them, it must be below the real one as well. And otherwise, I say I'm not sure. Okay, so this is what we need for these compression schemes. Because our goal is at the end to somehow at least correctly label all the sample, right? So I need to be able to do that. Okay, so how can we do that? I mean, I don't know. It seems, even in 3 dimensions, it doesn't seem so simple. Because think about it, what do you want really? So in 2 dimensions, so you get this body.
In 2 dimensions, you just get the W will be a cone.
Yes, in 2 dimensions we saw the answer, but somehow even in 3 dimensions,
The line, the set W will be just.
it won't necessarily be a cone. It will be this shape that separates 2 cones. All the lines that separate 2 cones.
No, I'm looking at the homogeneous case.
Yes. Yeah, I agree. No, the 2-dimensional homogeneous case is really 1-dimensional non-homogeneous, which is like 1-dimensional threshold. So this is too easy. Yeah. So really what we saw is like a 3-dimensional homogeneous case. So here's a dual problem that maybe you've seen in the past. So you're given a collection of dual just mean I replace points with hyperplanes and vice versa. Same thing, right? So now I give you a collection of hyperplanes, W1 up to W in d dimensions. There's a point that you don't know, right? And you want to predict, the sign of it given all these W's, right? What is this? This is just the hyperplane arrangement problem. So what is a hyperplane arrangement problem? So you're given a collection of hyperplanes, in space that you know, and there's some point that you don't know, and you want to find which region it belongs to, right? So again, hyperplanes partition space into regions, and you're allowed to make queries, and there's a point that you don't know where it is, and you want to find which region it belongs to. So you want to predict the sign of it compared to all the possible hyperplanes in your sample. And this is like one of the central problems in combinatorial discrete geometry, right? How to do that, algorithmically, information theoretically, and so on. But somehow, the nice thing here is that basically active compression schemes are exactly the same combinatorial object as what in this world is called a linear decision tree. So a linear decision tree for hyperplane region problem is exactly this process says, so I give you this, so just imagine, right? So you get all these points here, right? And there's a point that you don't know, and where is it? So I can ask you, is it above or below this line? You tell me below, so it has to be somewhat here. And then say, well, is it above or below this line? Below, it has to be here, and so on. So this is like a linear decision tree, which is exactly the same as what we allow, just in the dual world. But sort of, so now we can sort of fall back to this more known setting and say that, well, in fact, we just use non-results or linear decision trees to immediately get this, results for active learning, in high dimensions, using somehow general queries. But you see, somehow this is why it's not so trivial, right? For example, we don't know.
Still, assuming you're only allowed to query the planes from yours.
No, this is like allowed any point to query any point, right? So you get this. Think about here. So now the data points are like these lines, and what you don't know, the secret concept is this point, and you want to find which region it belongs to. So I'm allowing you to query any point that you want, right? Now you're allowed to query, is it here? You're allowed to. So basically, what you're allowed to query is the following question. So I choose any line that you want and query it above it or below it. So in this context, if you're only allowed to ask about lines from your sample, then there are lower bounds. This is impossible. You can't do things, non-trivially here. And it's basically the same example of the point of the dual thing. So you have to ask about other lines. So you somehow have to come up with new lines. So you've seen these 5 lines. Come up with a new line, maybe, this line here. Is it above this line or below this line? And you ask these type of questions, adaptively.
And then the answer is it's possible?
So it's possible, but it's not trivial. It's in 2 dimensions, it's simple. But in high dimensions, you can always do it.
Your scheme can be cast like this, where the lines are bisectors.
Not only by sectors, it could be whatever you want. I'll get to it in a second. Yeah, so there's an interesting question here, can you do it in high dimensions? And this will have nice applications. But the way these linear decision trees work, the way that people understand them now, they're not going to be bisectors, they're going to be arbitrary lines. And this is one of the downside of what we can do with linear decision trees. So here's one example how you can do it in high dimensions. So this is not the best that we know, but it's the first and the simplest one to describe. At least the description will fit in one slide. So how can I find these sort of lines here that sort of, would give me something, some interesting information? So what is the set? So how do we do it? So again, remind you of the setup. There are these known hyperplanes, W1 to Wm, and there's this unknown point, and I'm allowing these queries of either above or below certain hyperplanes. So let's first, and again, my goal is now somehow to query, so this is my small sample of size 40. So I'm allowed to query all these signs. So at least for my random sample of size 40, or whatever small constant I have, I query it above or below this point, these lines. So I query that. And now we construct a polytope. The polytope is just saying, let's say now I made some, just queries for these 40 points. So now this is not all my lines, it's just my small random sample, right? And now I know that it lies, let me just use a slightly bigger example. So now I know that it lies somehow, so I have this. I know that somehow it lies here. But I want the compressor knows it, but he wants to send this information to the reconstructor without specifying all these 40 whatever lines. He wants to specify a few points. So what should he do? He should say, well, my point is somewhere here, I don't know where, but if it belongs to this convex hull, it also belongs to some triangle that is supported there, right? I can always find 3 points in this case, in 2 dimensions, and maybe this point, this point, and this point, and say that, sort of belongs here, right? If I make enough queries, I will be able to find some triangle, or in D dimensions, a simplex, containing my point. So I don't really need to specify all these points here. I just need to specify 3 points. And to specify 3 points, each point is specified by 2 lines, right? So I don't really need all the original information. I can compress it. So in D dimensions, you construct a simplex that contains your point. So you make more queries to discover this simplex, but then somehow you discover it. You get the vertices of it are just vertices of the original polytopes. And then each vertex of delta or of P is just defined at the intersection of D hyperplanes. So you get D points. Each one is defined using D hyperplanes. So you just need D squared hyperplanes and some number of bits of side information, D squared log D. And that's all that you need to send to the constructor. You don't need to send the entire polytope where you started. So this sort of gives us an active compression scheme of cost whatever D squared, and it makes sort of, if you do the analysis, how many queries do I need to do to discover this simplex? Turns out it's like D to the 4. Okay? So I'm not going to describe this. But this already gives us automatically an active compression scheme. In general, dimension D. To think of D as a large constant 10, so you can do now active compressions in dimension 10, with log n many queries if you allowed arbitrary membership queries. And the reason this is exactly the same object as a linear decision tree with this 4 to the log n, which is what this work showed. This was about linear decision tree with the same object. And so this was in the 80s. Now the best that we know is get this 4 to roughly 2. So the most recent work is by Esther Ezra and Micha Sharir from last year, somehow improving this over the work a year before, they improving this from 4 to a 3, and now it's a 2. But it should be 1. The optimal is 1. So this is still open. Okay. So here there's nothing new. Technically, just this realization that these objects that we want to find in active learning for this half space problem are exactly the same problem that people have been studying for 30 years. So we just use them.
So this D squared log n is how much you send or how many queries you have to make?
How many queries you have to make. And I'm hiding some log factors there, like log D factors. So now there's this question about comparisons. Maybe we don't need to ask about general lines here. Maybe it's enough to use bisectors, right? And this sort of makes sense because this is really about comparing 2 points, which one is closer to the line, but now those are separated hyperplane in D dimensions. So here's my conjecture. That should suffice. So somehow, similar to the 2-dimensional case, it should suffice to do these comparisons. And sort of, and this will have this nice ML interpretation saying, no, if you want to do labeling in high dimensions, you don't need to ask. Because if you think about this sort of linear decision tree queries, they look really crazy. They look like, let's say you have documents, you want to label are they about sports or not. So this would look like, take this linear combination of these 5 documents, is it more or less about sports? Makes no sense, right? But comparisons make more sense, like which one is more about sports, right? Or maybe you get a score, 1 to 10, which one is like how confident you are. So it makes more sense.
It's like when you go to the eye doctor.
What?
It's like when you go to the eye doctor.
Yes. And instead of, I can phrase this as a purely geometric conjecture, so forgetting about machine learning altogether. So what's a conjecture here? So you have this set W, which is all your hyperplanes in D dimensions, and you define their polytope. It's just all these points act that lie the interior of this polytope, and you want somehow to compress this information, right? So so when we look at the different set of W minus W, it's just all these points W minus W prime. So all the differences of points in W, these will be our comparisons, or the bisectors. And here the conjecture. For every point X star in P, every point that you might choose here, I can always find a small subset of W minus W, a small set of bisectors of size linear in D, such that if you look at the polytope, all the X's that agree with W, or from this sort of small sample, small Q, they are a sub-polytope of P. So they don't go outside P. So this means if I make my predictions based on Q, they're going to be as reliable as what I make based on P. So this is, you can think about it for a second, this is exactly the condition of being confident, of never making mistakes on the sample or anywhere else. Okay? So you can think about that. This is what you get here. But now we get this sort of purely geometric conjecture. So in 2 dimensions it's true. Even in 3 dimensions, I don't know how to prove it. So think about it. You have this body in 3 dimensions, right? And you want to specify a pointer. So you're allowed to use all these bisectors for two faces. So they define some refinement of the Voronoi diagram there. And you want to choose some cell there. Not a minimal cell, but some cell inside it where the number of facets is only linear in 3 in this case. So even that, I don't know how to do. The time constant, I don't know how to do it. So, but I think it should be, it's an interesting question. And this will have 2 nice applications. So one application is what we discussed, is sort of, it will give this active learning for half spaces just based on comparisons. The other one is sort of, if you apply this to these problems in linear decision trees, like 3-sum problem, it will give this optimal or near optimal, solutions for them, sort of without actually doing things by hand. Use this generic method of doing the things.
But for that, you care about the constants or something?
No, they're somehow for n, so so the best will be like n to the 3/2, and this will give you n log n. Something like that. So the log is maybe not tight, but up to log factors, yeah. And maybe you can even shave the log by some.
What do you need to be the 3/2?
What?
What do you need to be the 3/2?
So that would be less than d to the 3/2. Right? So somehow here the trivial is take all of them, it's d squared, or not d, whatever, the size of w squared. So the size of w to the 3/2. I guess, yeah. Maybe that would be enough. But I'm not 100% sure. I need to think about it. So here's one sort of, so I'm not sure how much time I have. So I started, maybe I don't have time.
You can
I have, okay.
5 minutes.
5 minutes, yeah, 5, not even, yeah. So here's the one question. Are active compression schemes complete? I mean, if you want to understand active learning, is this all that we understand, or is this some limited model? So, in the learning, in the standard pack learning case, so we know that they are complete. So, I mean, it's enough to do active learning. And somehow, if you don't care about how visit dimension goes into how the dimensions of scales, then we know the answer here. And this was also pointed out this work of David Moran and Yudayev, but somehow we don't know it in the active learning setting. But one thing we can show that is in some sense already follows from previous work in this area, but somehow follows easier from our setup, is that if you don't allow membership queries, then they are complete. So if you go into the standard active learning model where there are no membership queries, then somehow, yeah, if you can do active learning in some way, non-trivially, you can also do it using this sample compression, active sample compression. But somehow it gives you this nice dichotomy that for standard active learning, either you can do a lot of things or nothing. And somehow this also follows from other combinatorial characterization, like this Haneke-Lang one. So it's not a new result, just maybe a different way of seeing this. So somehow so I just have 2 slides on it. So we have some concept class, and now we don't allow membership queries. And we have this prior free setting. So what's the theorem? Let's say there is some active learning algorithm that somehow to learn with error epsilon, it's sort of you get this sample of size like 1 over epsilon roughly, but it asks about much fewer points. Okay? Oh, sorry, the cost is much less than that. But let's say for us, let's say that sort of it makes a few queries, slightly less than trivial, doesn't query all the points. Then you can sort of boost it and get an active learning algorithm that learns error epsilon using just log 1 over epsilon. So whenever you have little O of 1 over epsilon queries, you can boost this to log 1 over epsilon. Okay? So that's when there are no membership queries allowed. And somehow this reduction doesn't work when there are membership queries. And the dichotomy is just, well, for the standard model of active learning, any concept class whatsoever, either active learning is useless, you basically need to query all the points, or it's sort of super useful, you need to query just log the number of points that you see. And what's the proof? The proof is basically here's like a proof sketch. It's not very hard. Well, first of all, choose epsilon original to be just something small enough, some constant small enough, so that you can perfectly learn a sample of size m using little O of m queries. And then active learning is the same as randomized, basically the same as a randomized decision tree, right? What is active learning? I query about point x1, then x5, then x3, so maybe I use some randomness, so I get this sort of decision tree. And sort of, the fact that it's sublinear means that each concept class has a constant size certificate. And this certificate in this learning literature is called teaching dimension. And this you can use to get this active compression scheme. So there's no deep combinatorics here, just of connecting some concepts together.
It's the same dichotomy that says that when you talk about VC dimension, you either have an exponential number of patterns on a particular set of samples, or it's polynomial.
Exactly. Exactly. Same thing. I agree. Exactly the same thing. That's true. So just to summarize, so we have these active compression schemes, this communication-based model for active learning. We don't know if it exists always without active learning, but we know that when it exists, whenever we can build it, it sort of saves exponentially the number of label queries. And sort of, we have this sort of communication model for what are simple queries that are not part of your part of your label set, or part of your data set. query whatever you want. I don't care. But you need somehow to send this information efficiently, right? So if I'm the compressor, and let's say Mark is the reconstructor, and I have got this endpoint, and I want to send him some information about some point that we haven't seen, I don't know how to send him the information about the point, right? So this would cost me a lot. So somehow I need some way, efficient way to describe it using a few original sample points plus a few bits of side information. So that's a restriction here. And I showed you this example application of doing half spaces, which just turned out to be exactly the same as linear decision trees. And my question is basically, what else can you do with it? So first of all, is it complete? What other applications can you have? So just a side note, we can also handle large margins, but let me sort of ignore that. So you can understand the geometric setting, what other examples could we have for interesting types of membership queries or other types of queries where this could be useful in practice, and somehow I really like this geometric conjecture. I mean, even if it's false, it's interesting to understand it. Okay, thank you.